Hello lovelies, in this video we're going to be going over the stuff you need for your exams in 2022. So this is for AQA Combined Science Foundation Chemistry Paper 1. If you are not doing that exact exam, then if you look in the description down below, there'll be the links to all the other versions. So the biology version, the higher version, the separate science version, they're all down below. There are also links to the new merch. Now in this video, I have looked at the advanced information and I've taken my video and I've taken my workbook and I've chopped stuff up and I moved stuff around so it matches what the exam board has told us is going to be on the exam. So we're going to start with the topics that are the major focus of the exam. Then we're going to move to the topics that are the required practicals, and at the end of the topics that aren't listed, so are probably going to come up as 1 or 2 marks. It does not include anything that the exam board has told us is not going to come up, so you don't need to worry about revising stuff that isn't on your exam. Good luck guys, we are going to get through this together. Metals are going to lose electrons, and when we lose electrons we get positive charges, and non-metals are going to be gaining electrons, and when we gain electrons we get negative charges. Things in group 1 are going to lose 1 electron, so are going to be +1 ions. Things in group 2 are going to lose 2 electrons, so are going to be +2 ions. Things in group 6 here are going to gain 2 electrons, so are going to be -2 ions, and things in group 7 are going to gain 1 electron, so are going to be -1 ions. This beautifully coloured periodic table is because of lots of different groups, lots of different categories on the periodic table. Group number 1 are also known as alkali metals. Group number 2 are the alkali earth metals or alkaline metals. Group 7 are the halogens, and group 8 are the noble gases. The big chunk in the middle are the transition metals. Our periodic table hasn't always looked like this. The first attempt at a periodic table was by Newlands in the 1800s. He tried to group things into octaves and rate them by pattern, which is a really good idea, except we have oxygen and iron in the same group, and they have very different properties. He arranged them by mass, but he didn't leave any gaps, and he tried to force things in to have similar patterns or properties as other things, and it didn't really work. Mendeleev was the next person to have a go. He also arranged things by mass, but the key thing is that he left gaps in his periodic table, and because he arranged things so that they were in groups with similar patterns, and he left gaps, he could predict the properties of elements that have yet to be discovered, and he was correct in his predictions. A few years after he developed his periodic table, a couple of new elements were discovered, and they fitted in really neatly, really nicely to his periodic table. So this week's table was accepted. It's changed ever so slightly by then. We now arrange things by electronic arrangement, but that's a very subtle difference. The group right on the far right hand side are group 8 or group 0. These are the noble gases. They have a full outer shell, and because they have a full outer shell, they don't want to gain or lose any electrons, which means they are really unreactive. And because they are unreactive, they actually have quite a lot of uses. Helium we use in balloons, and they are also used in neon lights, as you can see here in the amazing city of Osaka. Moving over one group to group 7, we have the halogens. We are still in the non-metals, and these are going to go around as diatomic molecules, which means their formula is going to be for chlorine gas Cl2, fluorine gas F2, bromine gas Br2. They're going to go around together in pairs. Because they only want to gain 1 electron, a nice easy way for them to do that is sharing an electron with something else that is the same. So fluorine here can easily gain an extra electron by sharing it with another fluorine. They are highly reactive because they only want to gain 1 electron. and the most reactive ones are going to be at the top. Boiling point is going to change as we move down the group. So things are going to have a low boiling point or a low melting point are going to be at the top. High boiling points or high melting points are going to be at the bottom. When they react, they're going to gain an electron, meaning they're going to form -1 ions, and gaining an electron is a reduction. They're going to react violently and rapidly with group 1 metals because group 1 metals want to lose 1 electrons. For example, sodium, which is a soft grey metal, will react very violently, very readily with chlorine, which is a yellow gas, to form sodium chloride, which is a white powder or salt. A more reactive element will displace a less reactive element. So here we have sodium iodide reactive with bromine. Iodine is here below bromine on the periodic table, so bromine is more reactive. So it will displace iodine in the compound, forming sodium bromide and iodine. Whereas if you try and react bromine gas with sodium chloride, chlorine is higher than bromine on the periodic table, so it's more reactive. You are going to get no reaction because bromine cannot displace chlorine out of this. These are commonly known as displacement reactions. The halogens are mostly used for sterilizing things. For example, chlorine, you're commonly going to know that as from swimming pools. Halogens want to gain 1 electron, so the most reactive ones are at the top. That's where there's least shielding between the electron they want to gain and the nucleus. Your alkali metals react very violently with water, and this is where you're going to see some flames coming from, some different colours coming from. This is one of the things that we use to make the different colours in fireworks. So the lovely lilac flame from potassium we can use in fireworks. If you've seen these in school, these are soft grey metals which are easily cuttable. They need to be kept in oil so it doesn't react with oxygen or with the water in the air because it's a very, very violent reaction. When the metal reacts with oxygen, we're going to get a metal oxide, which if you've seen these in school, when it was cut, it was shiny, but it soon started to dull. The dullness is the metal oxide. The metal plus water is going to form a metal hydroxide. This gives it its name, it's alkali metal, because the metal hydroxide is going to be alkaline. You can see that by the change in indicator if that's what your teacher did. And you will also notice this is a very exothermic reaction. It released a lot of heat. It also released hydrogen gas. That's what the fizzing was. The reactivity is most reactive at the bottom and least reactive at the top. Things at the bottom are going to have a low melting point or boiling point and a higher melting point or boiling point at the top. Alkali metals want to lose an electron, and the ones at the bottom are most reactive because there is more shielding between the electron that they want to use and the positive nucleus in the middle. Solids have a very, very fixed structure. Their atoms may wiggle a little bit, but it is around a fixed point. There is going to be some movement and some vibration, but they are not flowing at all, and they can't be compressed. Liquids have much more movement around, but they are not in a fixed position. They can flow, but they can't be compressed. Gases are very, very free to move. There's lots of movement going on in here. It is not around a fixed position. They do a lot of moving. They can flow and they can be compressed. Going from a solid to a liquid is melting. From a liquid to a gas is evaporating. Going in this direction, we are putting energy in. Going in the other direction, energy is coming out. So from gas to a liquid, it is condensing. From a liquid to a solid, we are freezing. A compound has a melting point of 19 degrees, melting point, and a boiling point of 74. Boiling point, what is the state at room temperature? Room temperature is about 27. So when it boils, it turns from a liquid into a gas. So above there, it is going to be a gas. And below there it is going to be a liquid. Melting point, we're turning from a solid, so this way is going to be a solid, and above there is going to be a liquid. So at room temperature it's going to be a liquid. Now the other important thing to remember about boiling point and melting point is that the opposite is the same number. So boiling point is equal to condensing point, and melting point is equal to freezing point. We just talk about boiling point and melting point instead of condensing point and freezing point. They are exactly the same number. So if the boiling point is 74, the condensing point is 74. If the melting point is 19, the freezing point is 19. State symbols tell us what state something is in. So an S is a solid, L is liquid, AQ is aqueous, and G is gas. If you see state symbols in an equation, the answer generally refers to them. If you see something that's liquid and liquid, or aqueous and aqueous going to a solid, it is going to turn cloudy. If you have a liquid and a solid, or a liquid and liquid and a gas is produced, you're going to see bubbles or a loss of mass, bubbles or fizzing. Here we have sodium chloride. Sodium are the grey bits you can see, and chlorine are the green bits you can see. The blue lines are the electrostatic interactions, the electrostatic attractions. Because the way we get you to draw ionic bonding is really false. It's not just one sodium combining with one chlorine. It is this massive, massive, massive lattice of sodiums and chlorines, or whatever we're looking at, bonding with everything else. So one sodium here isn't just going to be bonding with the chlorine next to it, or the chlorine that it's exchanged electrons to. It's going to be bonded with all of the other ones above it, next to it, behind it, in front of it, everything that it can reach. So this ionic bonding is a massive, massive, massive network, not just the small things that we get you to draw in class. So for ionic compounds, the structure is a giant ionic lattice. Properties, it is going to have a high melting point, high boiling point, and it is only going to conduct when molten or dissolved. This is because the ions need to be free to move. For simple covalent compounds, such as water, carbon dioxide, oxygen, nitrogen, hydrogen gas, hydrochloric acid, or methane, oxygen gas, or water, as we have here, they are very, very small structures. They have covalent bonding. Their properties is that they have low melting points and boiling points. They're generally going to be a gas at room temperature or a liquid at room temperature. They do not conduct electricity. For giant covalent compounds, ones made of carbon, such as graphite, diamond, or any fullerenes or silicon dioxide, they're going to have a giant covalent structure. Their properties are high melting and boiling points, and they do not conduct, and they do not dissolve. With polymers, whether they have crosslinks or not are going to determine what their properties are going to be like. So polymers that do have crosslinks are very, very fixed in place. These are going to burn upon heating, whereas polymers without crosslinks are going to melt upon heating, because these polymers can slide across each other, whereas these ones cannot slide across each other. Metals are made up of positive atoms in a sea of delocalized electrons, and these electrons being free to move is the reason that metal can conduct electricity, and why it's so good at conducting heat. An alloy looks slightly different to a metal. We still have our positive ions, we still have our delocalized electrons, but there's something else in there as well. This may be another metal it's alloyed with, or it may be something else like carbon that it's alloyed with. Pure metals have layers. Layers can slide across each other. Because they have layers and because they can slide across each other, they are soft. Alloys don't have layers, or they have distorted layers. And the distorted layers cannot slide. And because the distorted layers cannot slide, it means they are hard. Here we have diamond. It is a giant covalent compound, a giant covalent lattice. It is made of carbon, pure carbon, nothing else in there. And each carbon makes 4 bonds. So in the video you can see that the carbon is the black bits, the covalent bonds are the red bits, and each carbon is bonded to 4 other carbons. Obviously the ones on the edge aren't bonded to anything, but if you try and look in the middle, you can see that they are bonded to 4 other things. The properties of diamond that make it really useful is that it's incredibly hard. It's very rare, it's hard to find, it's also very beautiful, which makes it very precious. But the main thing is that it's incredibly hard, so we can use it in drills. Graphite is also a giant covalent compound. It is like diamond, pure carbon, but each carbon makes 3 bonds to other carbons, not 4 like in diamond. The properties are that it is soft and it conducts electricity. Because it is in sheets and there is a spare electron floating around in between these, that means it will conduct electricity. Graphite is what you find in pencils. Graphene is just a single sheet. If we were to compare diamond and graphite, they are both made of pure carbon. Graphite Graphite is made of 3 carbon-carbon bonds. Diamond is made of 4 carbon-carbon bonds. Graphite is soft, diamond is hard. Fullerenes are either carbon nanotubules or Buckminster fullerenes, which are balls. These are again all made of pure carbon. They make 3 carbon-carbon bonds, but unlike graphite, which is soft, these are incredibly hard. Buckminster fullerene can be used as a lubricant in things that need lubricating, like electrical cycles or some parts of machines. It can be used for reinforcement, so where you need a very, very strong, very, very light things like aircrafts or bicycles. They can also both be used, or in the future be used, for drug delivery. And fullerenes, carbon nanotubules, Buckminster fullerenes, there are loads and loads of potentials for these, but they haven't been realised yet. We can list the metals by how reactive they are, with the most reactive being at the top and the least reactive being at the bottom. Now you need to remember these. If you have any good mnemonics remembering these, you can pop these in the description below, in the comments below. That would really, really help other people. Things that are above carbon need electrolysis to be extracted, whereas things that are below carbon can just be extracted by reduction. However, things that are really, really unreactive, like silver, gold and copper, are generally found in the earth as their pure ores, unreacted with anything. Everything else is generally going to be reacted with oxygen in the form of metal oxides. You can also use this to predict the products from electrolysis. If the metal you are used in the electrolysis is more reactive than hydrogen, then you're going to get hydrogen as a gas. If it is less reactive, then you're going to get something else as a gas. And we can use this to predict the products for displacement reactions. If we reacted magnesium chloride with calcium, because calcium is more reactive than the magnesium, the calcium is going to take the place. So we are going to get calcium chloride plus magnesium as our products. However, if we reacted magnesium chloride with aluminium, because magnesium is more reactive, aluminium cannot take the place, it will not displace it, so no reaction is going to take place. You need to remember all of the equations, remember the ions, and be able to work out what is going to come from a reaction. So if we have an acid and a metal, we are going to get a salt plus hydrogen. Acid metal oxide is going to give us a salt plus water. Acid metal hydroxide is going to be a salt plus water. Acid metal base, salt plus water. Acid plus metal carbonate is going to give us a salt, water, and carbon dioxide. To work out the formula of the salts, you need to know the formula of all of your ions. I've made flashcards to help you with this. You can watch the video. I'm afraid you're going to need to watch it over and over again so that you learn it. And then you're going to need to make sure that you combine the ions in such a way that they are neutral overall. On the pH scale, things that have a pH 1 are acidic, pH 7 is neutral, and 14 is an alkali. The ions responsible for acidity are hydrogen ions. The ions responsibility for alkalinity are hydroxide ions. The neutralization equation is incredibly important. It comes up a lot, and that tells us that hydrogen ions plus hydroxide ions can be neutralized to produce water. To carry out titration, first of all you need to put 25 centimeters cubed in an alkali into a conical flask, add a phenolphthalein indicator or an indicator like methyl orange, fill a burette with an acid of a known concentration, take the initial reading on the burette and record it, and while swirling the flask use the tap to slowly add drop by drop the acid into the alkali. When the first permanent colour change happens, pink to clear for phenolphthalein, stop adding the acid. Record the final volume in the burette and repeat titers until you get it within 0.05 centimeters cubed. There are 2 indicators you can use for titrations. Phenolphthalein, which is the one you're seeing here, which in an alkali will be bright pink, and in an acid will be clear or colourless, or methyl orange, which in an alkali you can see it's going this yellowy colour, and in an acid will be bright red, giving us a neutralization point where it is an orange colour. Here we have sodium chloride. Now, ionic compounds have to be molten or dissolved to be able to conduct electricity, because it's when it's in its solid state you can see that this sodium and these chlorines are not going anywhere. they're very, very fixed. However, in a liquid or a molten or a dissolved state, when these ions are free to move around, that is when they're going to be conducting electricity, and that's when you can do electrolysis. Aluminium electrolysis is a slightly different form of electrolysis. We have one electrode up here, this is our positive anode, and another electrode down here, this is our negative cathode. The molten aluminium and the cryolite. Cryolite is just a compound that is added to reduce the melting point of molten aluminium oxide. It's added into this reaction vessel, and we get one reaction taking place down here and another reaction taking place at the top. At the bottom, at the negative cathode, we are going to be attracting the positive aluminium ions. They are going to be picking up electrons and turning into aluminium atoms. This is 3+, so it needs to pick up 3 electrons. And then at the top, at the carbon electrode, we are going to attract the negative oxygens. They are going to be losing electrons and turning into oxygen gas. Because we have 2 on this side, 2 oxygens on that side, we need 2 on that side, which means we now have 4 negative charges, we need to lose 4 electrons as well. This is a carbon electrode up here, and we are starting a reaction which causes oxygen gas to be evolved. Eventually the oxygen gas will react with the carbon electrode, and we are going to lose the electrode as carbon dioxide. So the carbon dioxide will wear away the electrode eventually, so this will need to be replaced. The molten aluminium collects at the bottom and can be taken off like that, and that is how we purify aluminium. For making a pure salt, we are going to be making copper sulfate. This is mixing sulfuric acid and copper oxide to make copper sulfate and water. You're going to need to heat the sulfuric acid, stir in the copper oxide, which is a black powder, until it is in excess, which basically means you can't dissolve it anymore. Let it cool a bit, and then you can filter the solution to remove the excess copper oxide, so that the black copper oxide powder will stay in the filter paper, and then the solution of copper sulfate will come out down the bottom. Once you have your solution of copper sulfate, you can evaporate away the water to leave you with the copper sulfate crystals. Now the size of the crystals will depend on how quickly you do this. You're going to be left with blue crystals. The blue crystals here are the hydrated ones, and the white crystals around the edge are the anhydrous ones. The common setups for electrolysis that you need to know are sodium chloride, sodium sulfate, copper chloride, and copper sulfate. For sodium chloride, the products you are going to get are hydrogen gas, chlorine gas, and sodium hydroxide. For sodium sulfate, the products you're going to get are going to be hydrogen and oxygen gas. For copper chloride, you are going to get copper and chlorine gas, and for copper sulfate you are going to get copper and oxygen gas. When we set up electrolysis, you need positive and negative electrode. Light bulb there just to check that electricity is flowing. You can see bubbles collecting around the positive and negative electrode. Sometimes this might be a metal collecting, as in the case of copper collecting here and here in copper sulfate and copper chloride. You can test for all of the different gases coming off, for example, hydrogen, chlorine, and oxygen. The test for hydrogen gas is a squeaky pop. The test for oxygen gas is relighting, glowing splint. And the test for chlorine gas is that it bleaches damp litmus paper. Here we have our wonderful, beautiful periodic table. It is a list of all the elements which are known to exist. Elements are a single type of atom. An atom's a very, very small thing. The word atom is actually Greek for uncuttable. And when they named them, they thought it was the smallest thing possible. The periodic table tells us loads and loads and loads of information about the elements, the range of elements that are known to exist. There are still loads yet to be discovered. A compound is 2 or more elements that are chemically bonded together. That's the important thing, chemically bonded together. Here we have the structure of an atom. We have electrons that are on the shells around the outside, protons that are in the middle, and neutrons that are in the middle. And this bit in the middle here is collectively called the nucleus. Protons are in the nucleus. They have a mass of 1 and a charge of +1. Neutrons are also in the nucleus. They have a mass of 1 and a charge of 0. Electrons are in the outer shells. Their mass is 1/2000 and they have a charge of -1. On the periodic table, you will see lots of boxes like this. This tells you all about the elements. This is the element's name, the symbol, and there are two numbers. This is the atomic number and this one is the mass number. Now for these, location doesn't matter. Different textbooks, different sheets are going to put them in different locations. The larger one is the mass number and the smaller one is the atomic number. The atomic number tells us the number of protons and the number of electrons in an atom. The mass number is the number of protons plus the number of neutrons. So here we have calcium. The smaller number is the atomic number. The large number is the mass number. And if you want to find the number of protons, it is simply the atomic number. So in this case, 20. The number of electrons is also the atomic number, so again 20. The neutrons is the mass number, which is 40, minus the atomic number, which is 20, equaling 20. You need to be able to take a set of words and turn it into a balanced symbol equation. So there is quite a lot for you to do here because you need to remember the chemical symbols for quite a large number of things. Water is H2O. That turns into hydrogen gas, which is going to be H2, plus oxygen gas, which is going to be O2. And now we need to balance it. Draw a line down the middle, circle everything, and list what we have. We have hydrogen, we have oxygen, we have hydrogen, we have oxygen. Count the number of things. 2 hydrogens, 1 oxygen. 2 hydrogens, 2 oxygens, sorry. So we need to increase the number of oxygens on this side because you see there aren't enough. Then we have to add another H2O, put that in a circle, redo our numbers. We now have 4 hydrogens and 2 oxygens. So our oxygens are balanced, but now our hydrogens, we have more on this side than we do on this side, so we need to add more hydrogens here. Again, the only thing we can do is to add a whole another bubble. We now have 2 hydrogens here, 2 hydrogens here, making 4 in total and 2 oxygens. So now we have 4 hydrogens on this side, 2 oxygens, 4 hydrogens and 2 oxygens. We need to rewrite that neatly for the examiner, so we have 2 bubbles of H2O turning into 2 bubbles of H2 plus 1 of O2. I seriously recommend you learn at least these formula. Carbon dioxide is CO2, water, H2O, oxygen gas, O2, hydrogen gas, H2, nitrogen gas, N2, ammonia, NH3, hydrochloric acid, HCl, sulfuric acid is H2SO4. Elements, pure things. Compounds, 2 or more different things chemically bonded together. Mixture, lots of different things, some of them chemically bonded, some of them not. When you have mixtures and you want to separate them, there are a number of different things you can do. Distillation, where you're going to separate things off by boiling point, so things that have a different boiling point will distill at different temperatures. Evaporation, where we are going to remove the liquid and leave solids that have been dissolved in the liquid in the dish. Filtration, where we have large particles of solid in the liquid. The particles of solid will stay in the filter paper and the liquid will drip through. And fractional distillation, where you can take things off at different boiling points. We haven't always known that an atom had a nucleus and electrons orbiting around the outside. We used to have a plum pudding model, where we had a large cloud of positive charge with negative electrons dotted throughout, a bit like a Christmas pudding, which is why it's called the plum pudding model. Rutherford and Marsden did an experiment to test the plum pudding model. They took an alpha particle gun, and alpha particles are positively charged, and they had a sheet of very thin gold foil. And what they did is they fired alpha particles at this sheet, and the majority of them went straight through, which was a bit weird. Some of them got deflected a little bit, and some of them got deflected a massive amount. And this suggested that there was a centre which was positive, a small part that was positive, and then a large section all around which was negative. And this led to the development by Bohr of the nuclear model that we use today. The model of atoms changed quite a lot over time. You don't need to know all the details of this, you need to know that Rutherford was responsible responsible for discovering the nucleus and protons, that Chadwick discovered neutrons, and that Bohr is our current, or developed our current model. The periodic table gives us loads and loads of information. The first bit of information it gives us are about groups. Now groups go down the periodic table. Group 1, Group 2, 3, 4, 5, 6, 7, 8, or Group 0. Groups tell us the number of electrons on the outer shell. So things in Group 1 are going to have 1 electron in the outer shell. Things in Group 2 are going to have 2 electrons in the outer shell. Group 6, 6 electrons in the outer shell. Group 7, 7 electrons in the outer shell. Periods go across the periodic table. So here is our first period, the one that everyone always forgets because it's only got hydrogen and helium in. Here is our second period. Here is our third period. And the periods relate to the number of shells that things have. They also remind us how many electrons there are in each shell. So in the first period there are 2 elements, which means there are going to be 2 electrons in that shell. In the second period there are 1, 2, 3, 4, 5, 6, 7, 8 elements, which means there are going to be 8 electrons in that shell. And we can use this information to tell us about the electronic configuration. Here we have magnesium. Here is magnesium on the periodic table, and we can see that the number of electrons it has is 12. It is in group 2, and it is in period 3. So that tells us it has 12 electrons in total. It has 2 electrons on the outer shell because it's in group number 2, and it has 3 shells because it is in period number 3. So when we want to draw the electronic configuration of magnesium, we know it's in period 3. It's going to have 3 shells. The first thing we can do is draw 3 shells. 2, 1, 2 go on the first shell. 1, 2, 3, 4, 5, 6, 7, 8 go on the second shell. That's the most that can fit in that shell. That brings us up to 10. 10, 11, 12, 2 electrons on the outer shell. From the periods, we know that the first shell can hold a maximum of 2 electrons, the second shell can hold a maximum of 8 electrons, the third shell can hold a maximum of 8 electrons, and then you only need to know up to calcium, so another 2 for your GCSE. Here we have sodium, and it has an atomic number of 11, which means it's going to have 11 protons in the nucleus, and protons have a positive charge. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now in the atom it has 11 electrons drawn on here. Electrons have a negative charge. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now in an atom, the positive charges and the negative charges cancel each other out, so the overall charge on the atom is going to be 0. However, when sodium makes an ion, this electron here goes away. So it still has the same number of protons, it's still sodium. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. But it's lost an electron. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it has 1 more proton than it has an electron, meaning this is going to have an overall positive charge. Ionic bonding is the transfer of electrons from a metal, which is on this side of the periodic table, to a non-metal on this side of the periodic table. Anything that is in group 1 is going to form a +1 ion, group 2 a +2 ion, group 6 a -2 ion, group 7 a -1 ion. Here we're going to make magnesium oxide. Magnesium is in group 2, so it has 2 electrons in its outer shell. Oxygen is in group 6, so it has 6 electrons on its outer shell. In ionic bonding, oxygen is going to keep the electrons that it's already had, and the electrons that were with magnesium are going to be transferred to oxygen. We call these dot and cross diagrams because one element has a dot for electrons and the other element has a cross for electrons. We then draw square brackets around these and indicate the charge. So magnesium has lost 2 electrons, so it's going to have a +2 charge. Oxygen has gained 2 electrons, so it's going to have a -2 charge. Covalent bonding is the sharing of electrons between 2 non-metals, these up here. And these are the common ones you need to know how to draw. For each of these, you need to be able to give the name, the formula, be able to draw it with lines, and be able to draw the dot and cross diagram. So hydrochloric acid or hydrogen chloride, 1 element of hydrogen, 1 element of chlorine. Ammonia, NH3, nitrogen in the middle, 3 hydrogens coming off around the side, methane, CH4, carbon in the middle, 4 hydrogens branching off it, hydrogen, H2, very simple one there, chlorine, halogens go around as diatomic molecules, oxygen, we're getting a bit tricky now, has a double bond. Each line is equal to a pair of electrons. Here we have 2 lines, that is 2 pairs of electrons. We need 4 electrons being shared in the middle, and nitrogen has a triple bond, 2, 4, 6 electrons being shared in the middle. If in the exam they give you a picture and ask you to link the formula of it, you simply need to list what we have. So in the first one we have carbon and we have hydrogen, and then we need to count them. 1, 2, 3, 4, 5, carbon, 5, hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Last one, carbon, hydrogen, oxygen, we have 1, 2, 3 carbons, 1, 2, 3, 4, 5, 6, 7, 8 hydrogens, and 1 oxygen, so we don't need to put a number after that. It's really important that you write things in the right size and in the right place. So that is incorrect because your numbers are too big. That is incorrect because your numbers are in the wrong place. You can measure the mass or volume of a reactant or product by collecting the product, say in a gas syringe, or using a scale or balance to look at how the mass changes as a reaction progresses. Whenever you are measuring something, there is going to be a degree of uncertainty, whether it's a burette, a measuring cylinder, or a beaker. You need to look for the bottom of the meniscus always, because there is going to be this difference, this dip between where it looks at the top and where it is at the bottom. And you can say whether it is on the line or in between the line, but you can never say that accurately because it might be a quarter of the way or 3/4 of the way to the next line. So while you try and measure things accurately as you can, there is always going to be a degree of uncertainty. When we are working out concentration, that is going to be your amount divided by your volume. Concentration is measured in moles per decimeter cubed, amount is in moles, and your volume is in decimeter cubed. The new style exams means there are a lot of wordy questions that incorporate a lot of skills all at once. In this question, you need to first of all recall the formula for things, then balance the equation. So hydrochloric acid is HCl, magnesium is Mg. Now we need to work out the products and the formula of the salts. A metal plus an acid is going to give us salts plus hydrogen. Hydrogen's the easy bit. It is H and then 2 because it goes around as a diatomic molecule. The salt is going to be magnesium chloride, but we need to know that magnesium is a 2+ ion and chlorine is a 1- ion. So it needs to be MgCl2 so that there are 2 negative ions for each positive ion. Now this is brought in a lot of skills, recall of the formulas, working out the salts, the product, so working out what type of equation it is. And then after all of that, we need to balance it. So to balance our equation, we draw a line down the middle, list what we have, hydrogen, chlorine, magnesium, hydrogen, chlorine, magnesium. It is really going to help you if you keep things in the same order. Circle the compounds that we have. List the numbers of things. So we have 1 hydrogen, 1 chlorine, 1 magnesium, 2 hydrogens, 2 chlorines, 1 magnesium. So you can see straight away we need some more hydrogens and some more chlorines. The easiest way for us to do that is to add another HCl on there. Then redoing our numbers, we have 2 hydrogens and 2 chlorines. That is balanced. Writing it out neatly for the examiners, because just leaving it like this won't get you the marks. We have 2 bubbles of hydrochloric acid plus magnesium turns into magnesium chloride plus hydrogen. When you are working out the MR, which is the relative formula mass, you need to take all of the ARs, which is the relative atomic masses, and add them together. Now the mass, remember, is the larger number of the two. Doesn't matter where it's located, it is the larger number of the two. So hydrogen has a mass of 1 and we have 2 of them. Sulfur has a mass of 32. Oxygen has a mass of 16 and we have 4 oxygens. So 1 times 2 is 2 plus 32 plus 16 times 4, which is 64. Add those together, we get 98. An endothermic reaction feels like it gets colder, whereas an exothermic reaction, you can feel it gets hotter. Another way of saying gets colder would be to take heat in, and another way to say get hotter would be to give heat out. Now we can make these slightly more sophisticated by replacing the word heat with the word energy. So now a sophisticated answer is that an endothermic reaction takes energy in and an exothermic reaction gives energy out. During an endothermic reaction, energy is going to get taken in, so we have our reactants down here. Energy gets taken in, so our products are up here. So we can say that the energy of the products is higher than the energy reactants. During an exothermic reaction, energy reaction is given out, so our reactants, energy is given out. So our products are going to be down here, which means our products have lower energy than the reactants. For example, an endothermic reaction would be electrolysis. An exothermic reaction would be burning or neutralization.